In this lecture, we are going to introduce the blow-up of the plane at a point. We consider the plane, we remove the origin from the plane, and then we replace the origin with the directions of approximation to the origin. More precisely, we are replacing the origin with a real projective line. And we are going to use the techniques that we studied in the last lectures in order to prove that this construction that I just presented provides a real analytic manifold. This real analytic manifold is very interesting. It is true that on the one hand, it's more complicated than the plane. For instance, our new manifold is non-orientable, whereas the plane is. But there are some advantages too. There is a natural way of lifting objects from the plane to this new space, and the lifts many times are simpler than the original space. Indeed, sometimes the lifts of singular objects, for instance, the image of an immersion of the line in the plane that is not submanifold, can be transformed into much simpler objects, for instance, a submanifold. And we'll see that this happens with a picture. Okay, we're going to replace the origin of the plane with the directions of approximation to the origin. This transformation, in particular, separates curves that converge to the origin tending to different directions. And for instance, it's going to separate the lines through the origin. For instance, the two axes, x equals 0 and y equals 0. Let's, first of all, let's have a picture here. So the picture over here is a neighborhood of the origin in the plane. And this is going to be the blow up. This point is going to be replaced by this line over here. Indeed, it's not, it's a circle that we are focusing here in a local picture in a neighborhood of a point. And what we have is that these lines are separated. This transformation is very interesting. For instance, it is used in desingularization, and the picture gives an idea of why. If you consider this curve over here, as we saw before, this curve is not a submanifold. Okay, here we have a problem at this point, at the origin, which is what is called usually a node, and also a singular point. But what happens locally is that there are two local branches of the curve going through that point. And in the picture, the tangent spaces at these two local branches are different. So when you actually lift this curve to the blow up of the origin, what happens is that this curve is transformed into this one. And when you get through this point, when you follow the curve and you get here, you're getting to this point, then you continue, you have this, and instead of going twice through the same point, in the blow up, you are going through two different points. So you transform now something that it is not a submanifold of the plane into something that it is a submanifold not of the plane, but of this blow up manifold. So it is an interesting transformation because it allows to transform objects that are singular into objects that are not. Okay, but yeah, this is something that it's nice to discuss, but how do we define properly this manifold, the blow up of the plane at a point? Okay, so what we are going to do is considering this map from the complementary of the origin in the plane to the product of the plane and the real projective space of dimension 1, which is indeed a circle. And we are sending xy to the pair xy, and here the point defined the projective space by xy. That's one reason, because we have to exclude the origin, because it's not defined any point in here. So we are in a situation in which apparently we are doing nothing, because we are considering xy and then its class in the projective line. But of course, the class is completely determined by xy, so we are introducing redundant information apparently. Okay. What happens is that the blow up of the plane at the origin is by definition the closure of the image of this map. Okay? Let's study this a little bit more. What happens, of course, is that, as we said, if we consider points outside of the origin, we're not doing much, because here we are considering the point and then something that completely depends on the point. So this map tau is actually a diffeomorphism between the complementary of the origin in the plane and a submanifold, real analytic submanifold of R2 times the projective line. Okay, so essentially outside of the origin, we're not doing anything, as we can expect. But what are the points that we are introducing? If you fix one class, of course, these points are contained in the points that are have the first element of the pair is 0, 0, and the second belongs to the real projective line. But this is not just an inclusion, it's an equality. Because if you consider a point of the form second 0, 0, and here x0, y0, this point is always going to be in the closure of the image, right? Because we have just to consider the limit of t times x0, y0, and here the class of t times x0, y0, right? When t goes to 0. That point is going to be in the closure of the image. What happens is that we can actually remove the t from here, because that doesn't change the point in the projective space at all. So we can actually consider here x0, y0, and when t tends to 0, the first component of the pair converges to 0. So this limit is going to be the point 0, 0, and here the class of x0, y0. So indeed, what we proved is that every point in here is actually in the difference between the blow up of the plane of the origin and the image. Here it's not the image of R2, because tau is not defined in R2. Here, to be more precise, should be the image of R2 minus the origin. But it's defining that difference. So as we said, we are adding something that is a real projective line, and the real projective line is a circle. we are removing the origin and adding a circle. Is this manifold? And how can we show this without working too much, without actually doing too many calculations? Let's see it. Okay, so we have here the map tau, and we are going to consider an atlas of the product of the plane and the real projective line with two local charts. R2 has an atlas that has just one chart, which is the identity map. And we saw that the projective eyes of R2 is a manifold that has two natural charts. So because of that, the Cartesian product is going to have an atlas with 1 times 2, in other words, two charts. The domains of the local charts are going to be R2 times U1, where U1 is the set of points in the real projective line such that the first coordinate is different than 0. And the domain of the second local chart is going to be R2 times U2, where U2 is the set of classes of the real projective line such that the second coordinate is non-vanishing. And we can consider the two local charts. The image of UV and the class of XY, it's going to be in the first component of the pair. Yeah, it's just the identity, because the identity is the local chart for R2. So the first component of the pair is UB. And then we have to consider the local chart for U1. And the expression of this local chart is sending the point at the class of XY to Y over X. This is the first chart. Analogously, we are going to have a second chart whose formula is going to be given by this expression. We are sending UB and the class of XY to UB and X over Y. This is well defined, of course, because Y is different than 0. So we have these two local charts, and we can actually try to write down the equations of this blow-up set, the blow-up of R2, in these two local charts. Okay? What happens is that if you consider a point over here, in order to be in the image, these 2 points, the class of this point in the real projective line has to be this point. And this happens if U times Y is equal to B times X. So this is the equation. But of course, we want to write it down in local charts. In local charts, we have that there is a coordinate that is Y over X. So we divide here by X, and we get the coordinate, let's call it T. And in these local coordinates, in the first local chart, the blow up of the plane at a point has an equation which is U times T minus B equal to 0. Okay? But what happens is that this map over here, as a map from R3 to R, is submersion. So the preimage of 0 is actually going to be a submanifold of this space. This space has dimension 3, and this is going to be a submanifold of codimension 1, or in other words, of dimension 2. So in the first local chart, we have that the blow up of the plane at 0 is actually a submanifold. That the equation of this blow up at the second local chart is also easy to find, because instead of dividing here by x, we divide by y. And we get, yes, we get u minus s times p equals 0. Again, this function is submersion, so the same arguments show that in the domain of the second local chart, which is an open subset of R2 times the real projective line, our blow-up set, the blow-up of the plane at the origin, is still a submanifold. So it's going to be a submanifold, and in particular, a manifold. So we get that the blow-up of the plane at a point is a manifold of dimension 2. We actually took away the origin, we replaced the origin with circle, and we got a different manifold. This manifold is going to be real analytic because all the manifolds in this construction and the functions that we are considering are all real analytic. And as I said, the dimension is 2. Something that it is very interesting about this manifold is that, for instance, let's consider first here the vertical line. And let's put here the vertical line. And we actually, we move in clockwise sense. Okay, it would be something like this. So what happens is that we are going to have in the blow up all these lines. But at some point, we're going to do half a turn. And when we do half a turn, we get to the initial line. Because if we consider a line and we rotate 180 degrees, we have the same line. So after rotating p radians, okay, we get to the initial line, to the initial vertical line. But what happens is that if we consider a point in here and we follow that point, okay, what we get, okay, we have here this point, at the end we get this point. But this point in the initial line is not in the top side, it's in the bottom side. So when we have, what's going to happen when we identify points is that we have to identify this point with this one. And for instance, we have to identify this point over here with this one. Okay? We have to identify a point here that it is in the top side with a point that is here in the bottom side. But that's going to give to us a Möbius band. So this blow up of the plane at the origin is not going to be an orientable manifold. We want to understand, at least with a picture, how a neighborhood of this real projective line that we are adding is. And what we have is that we're going to be in this situation. This is going to be a neighborhood of this line, the real projective line, and indeed the line is going to be like this. So what happens, because that's what we can deduce from the previous picture, right? If we consider a point here, let's say in the bottom, below the origin, what happens is that if we travel along the picture, okay, what we get is that we untapped in the top side. And that means that a neighborhood of this real projective line that replaces the origin is a Möbius strip. So we are actually, our new manifold is not anymore orientable. It is more complicated. A neighborhood of the origin, which is as simple as it can get as manifold, is now transformed into a Möbius strip. But as we said, this construction is interesting because even if the new space is clearly more complicated, some objects become simpler. And let's refer again to this curve over here that can be lifted to this curve, which is now a submanifold of the blow-up of the plane at a point. So far in this course, we defined differentiable manifolds and differentiable maps, and we studied the properties of immersions and submersions. From the next lecture on, we are going to introduce the most important concept in this course, namely transversality. And we are going to exploit this powerful tool from very early on. For instance, by using transversality, we are going to prove the Whitney embedding theorem that says that if you have an X-ray manifold, that it is actually Hausdorff and second countable, then you can embed it in a Euclidean space. And you can do it in a Euclidean space whose dimension is at most twice the dimension of the X-ray manifold plus 1. Thank you for your attention.